Hi, this is Sonia Doucette. In this video, I'll show you how to calculate the pH and the concentration of all species present for a solution of known molarity for a monoprotic acid. And this is going to be a case where you have to use the quadratic equation to find your solutions. This problem asks you to calculate the pH and equilibrium concentrations of all species present in a 0.010 molar nitrous acid solution at 25 degrees Celsius. The first thing you want to do here is to determine species present initially and their acid-base properties. You know that nitrous acid is initially present and that it is an acid, and water is also present because we're talking about a solution of nitrous acid in water, and water can act as an acid or a base. So those are your species present and their acid-base properties. Now you want to determine the possible proton transfer reactions so that you can figure out which is the principal reaction and will therefore head your ice table. So the possible proton transfer reactions are when our acid, or one of our acids, nitrous acid, transfers a proton to a base present, and water can act as a base. And when that happens, you're left with hydronium ions and the conjugate base of nitrous acid, which is nitrite. The Ka for this reaction is 4.5 times 10 to the negative 4. The other possible proton transfer reaction is where a proton is transferred from one water molecule to another water molecule, and this is because water can act as both an acid and a base. And what you're left over with when this happens is a hydronium ion, which results when one of the waters accepts a proton, and a hydroxide ion, which is left over when the other water molecule has donated a proton. And the equilibrium, or K value, for this proton transfer is given a special designation of Kw, or the ion product constant for water. And we know that this is 1.0 times 10 to the negative 14th. Because the principal reaction is defined as the reaction with the larger Ka value, we know that the first reaction drawn here is going to be our principal reaction, and that the other proton transfer reaction, where water transfers a proton to water, will be the subsidiary reaction. So the principal reaction is going to head the ice table. So let's draw the ice table. We have our principal reaction at the top of the ice table. And then we have our three rows where we have the initial concentrations of all species present, the change in those concentrations that the species undergo when they reach equilibrium, and the equilibrium concentrations of all those species. We're given in this problem that the initial concentration of nitrous acid is 0.010. We don't have a concentration of water because it's a pure liquid. The hydronium ion concentration to start is approximately 0. There's always some hydronium ion present in pure water, but not as much as what will be present once we've added the acid, in this case nitrous acid. And then we have 0 conjugate base present, or nitrite ion, because we start only with nitrous acid and water. The change in these concentrations to reach equilibrium will be minus x for nitrous acid, because some of that nitrous acid will be lost when it donates a proton to water. And on the other side, because for every 1 mole of nitrous acid lost, we gain a mole of hydronium ion and nitrite ion due to the stoichiometry of this balanced equation. We'll have a plus x for hydronium ion and a plus x for nitrite on the other side. And then the equilibrium concentrations in terms of x will then be 0.010 minus x for nitrous acid, and then x for both hydronium ion concentration at equilibrium and nitrite concentration at equilibrium. So to solve for x here, we write the equilibrium equation, which is going to be Ka is equal to the hydronium ion concentration multiplied by the nitrite ion concentration divided by the nitrous acid concentration. We know the Ka value because we look it up in a table, and we find it to be 4.5 times 10 to the negative 4, and that's going to be equal to the hydronium ion concentration, which we designated as X in our ice table, multiplied by the nitrite ion concentration as designated in the ice table, and then divide that by the nitrous acid concentration, which is 0.010 minus X in our ice table. So now we need to use this equation to solve for X. And remember that it's a good idea to try to get rid of the X on the bottom in the denominator here, because it can make solving this equation for X a lot easier. So if we can do that, it's a good thing. So what we're going to do to try to do that is make an assumption. We're going to assume that 0.010 minus X is pretty much equal to 0.010. So basically what we're saying is subtracting X from 0.010, or the initial concentration of nitrous acid, is not going to change the initial concentration of nitrous acid because it's so small. So in order to test this, we're going to rewrite this equation, substituting in 0.010 into the denominator and getting rid of that X, and see how it goes. So we have 4.5 times 10 to the negative 4 is equal to X squared divided by 0.010. Multiplying both sides by 0.010, we're left with X squared is equal to 4.5 times 10 to the negative 6th, and taking the square root of that number will give us X is equal to 2.1213 times 10 to the negative 3. So now that we have our X, we want to test the assumption that we've made. So to test this assumption, all we're going to do is substitute in our X value to the equilibrium concentration here to see if the equilibrium concentration, or the initial concentration, will be changed by substituting in that X value. Negative 3, and then what we get when we do the math here is 7.87 times 10 to the negative 3, written out in decimal form, will give us 0.0079, and this is also rounded to the correct number of significant figures, and you can see that this value is different than the initial concentration of 0.010. So that means we cannot make this assumption, and we need to use the quadratic equation to solve for X in this case. So let's go back to our original expression and go on from here using the quadratic equation. So what we have is 4.5 times 10 to the negative 4 is equal to X squared over 0.010 minus X. Multiply both sides by the denominator, and we have 4.5 times 10 to the negative 4 times 0.010 minus X is equal to X squared. Multiplying out the parentheses, we're left with 4.5 times 10 to the negative 6th minus 4.5 times 10 to the negative 4. X is equal to X squared. So in order to use the quadratic equation, we want to get this in the general form of ax squared plus bx plus c equals 0. So we move everything over to the side where the x squared is, and we'll be left with x squared plus 4.5 times 10 to the negative 4x minus 4.5 times 10 to the negative 6 is equal to 0. So from this, we know that A is equal to 1, B is equal to 4.5 times 10 to the negative 4, and C is equal to negative 4.5 times 10 to the negative 6. So we've just taken the coefficients here, which for the x squared value, we have a coefficient of 1. For the x value, we have 4.5 times 10 to the negative 4, and then C is by itself as a negative 4.5 times 10 to the negative 6th. So now that we have the A, B, and C values, we can actually use the quadratic equation to solve for this. So the quadratic equation is x is equal to minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. And we have to solve for two cases here. The case where we have a plus and the case where we have a minus. So let's do the plus case first. And in this case, x is equal to negative 4.5 times 10 to the negative 4. So we're substituting in our a, b, and c values here, plus the square root of 4.5 times 10 to the negative 4 squared minus 4 times 1 times negative 4.5 times 10 to the negative 6. And that will all be divided by 2 times 1. So when you do the math here, you'll find that x is equal to 0.0019082. Solving for the minus case, we have x being equal to negative 4.5 times 10 to the negative 4 minus the square root of 4.5 times 10 to the negative 4 squared minus 4 times 1 times negative 4.5 times 10 to the negative 6th. And all of this, again, will be divided by 2 times 1. And when you solve for x and do the math here, you get a negative 0.0023582. So if you look back at the ice table, the hydronium ion concentration and the nitrite ion concentration are both directly equal to x. And having a negative concentration just doesn't make any sense physically. So we can get rid of this value, and by doing that, we know that this is going to be the value of x that we'll use to solve for the concentration of all the other species present. So we'll use this value and go back to the ice table, and when you do that, you can see that we've designated both the hydronium ion concentration and the nitrite ion concentration as being equal to x, and when we round to the correct number of significant figures, we find that we get 0.0019 molar for those two concentrations. We also need to find the nitrous acid concentration, and according to the ice table, in terms of x, it's equal to 0.010 minus x. So we do 0.010 minus the value we found for x, which is 0.0019082. When you do the math and round to the correct number of significant figures, you'll find that you have 0.0081 molar for your concentration of nitrous acid. We also need to solve for the hydronium ion concentration. To do that, we know the relationship Kw is equal to hydronium ion concentration multiplied by hydroxide ion concentration. So now we're going to solve for hydroxide ion concentration by flipping this relationship around and saying that the hydroxide ion concentration is equal to Kw divided by the hydronium ion concentration, which is what we just solved for. Kw we know is 1.0 times 10 to the negative 14th. Hydronium ion concentration we're going to say is 0.0019082, so we're not going to round too early here to prevent rounding error. And when we do the math and round to the correct number significant figures, we have 5.2 times 10 to the negative 12th molar for our hydroxide ion concentration. So those are the concentrations of all species present: hydronium ion, nitrite, nitrous acid, and hydroxide ion. And the last thing you need to do here is solve for pH. So you know pH is equal to the negative log of the hydronium ion concentration. So all you need to do is substitute in your known hydronium ion concentration, which is 0.0019082. Again, not rounding too early to prevent rounding error. And when you do the math there, you find a pH of 2.72. So there is your pH for this problem, and you've solved for everything you've needed to, so you're done.